All right. So, to start studying the power flow in an electromagnetic wave, um, I would like to start by saying that much of what I am going to be discussing is from the Feynman lectures on physics. Um, this is chapter 27, and I highly encourage all students who are watching this course to please try to get the 27th chapter and at least read the first 4 sections, right? So 27, chapter 27, sections 1 to 4, right? I believe a take on the power flow for electromagnetic wave has been very well done by Dr. Feynman. Nevertheless, some aspects of that discussion we'll look at here, right, in terms of deriving the power flow for electromagnetic waves. So, the argument starts something like this, right. So, just like for the conservation of charges, we wrote that we wrote the continuity equation dou rho by dou t plus the divergence of the current density is 0, right. What this essentially told was, if there were a rate of change of the charge density in a certain volume, it has to most likely be that these charges are escaping the volume, constituting a certain current flux or charge flux, right. So, similarly, we believe that energy conservation also should have this kind of an equation, right, because we do not presume that energy can be destroyed in one location and magically reappear in another location that is quite distant, right. So, energy, if it has decreased in a certain volume at a particular location, it's most likely that it flowed from that point to a different point, right. So, we say that energy conservation is also a local process. Okay, so we expect there to be an equation where we will call U as the energy density and P as power flow per unit area. Right. We as yet do not know what U and P are, but if I were to just mimic the charge conservation, I would end up with an equation like this. But this does not seem to be complete, right. The issue happens to be that we have trouble around sources and detectors, right. So, if I have a light bulb or a camera or a photo detector, around these points I see that the radiation density kind of vanishes or is getting created, right. So, around sources I am seeing new electromagnetic waves being created, and around detectors I am seeing these electromagnetic waves are being destroyed, right. So, the so called sources and sinks of electromagnetic waves do not quite satisfy this, right. Feynman gives a very nice example by saying that if you walk into a dark room, there is no light, so there is no electromagnetic wave energy in that volume, and then you flip a switch and then suddenly the room is full of light, right? So the key to understand is that the generation or collection of light involves an exchange of energy between matter and electromagnetic radiation, right? So we'll have to somehow incorporate that into this equation, because if light has been emitted from a certain source, the source must have lost its energy, right? And from Einstein's relation relating energy and mass, the source must have lost some mass. Right? So we say that the field energy alone is not conserved. Right? So we can say that field energy plus energy of matter is conserved. Right? This is akin to saying that the overall energy in the universe is constant. Right? So let's consider a volume right, and we'll say that the integral of u dv over this volume V is the field energy, the total field energy. U is the energy density, and when integrated over the entire volume, you get the net field energy. Right? So if I were to incorporate this integral in our equation that we have come up with, we have something plus work done on matter inside V. Right? So now we have to find out what this work done on matter inside V is, right? So here is a very important point that I would like to mention to all students. This is one of the most basic ideas. We covered this early in the introduction also, but I am trying to emphasize this again, that the source of all electromagnetic waves are accelerating charges. Right? So I will repeat that. Any electromagnetic wave you might see anywhere in the electromagnetic spectrum, a charge must have accelerated to cause those electromagnetic waves to exist. Right? So there is no other form or way of generating electromagnetic waves. Keep this in mind. Right? As to how this electron is accelerating or where it is accelerating is a very exciting notion that you can try to explore in whichever stream you may choose to pursue in your future. Right? So if I turn on a light bulb, which electron is oscillating and what is the rate of acceleration in order to get the frequency of light that it is emitting. Right? All these are very exciting questions to ask yourself, even the light from the sun. Right? So we are going to say that in order to get the work done, right, on matter, we are going to go back to our force equation on charges. right. So, this is the force experienced by a charge q in a region with electric field E and magnetic field B, or I should say magnetic flux density B. The rate of doing work is F dot V, right. So, when I take the dot product of the first equation with V, I essentially get right. So, from our discussion on vector algebra, you should know that this is 0 because V cross B is a vector that is perpendicular to both V and B, and when I take such a vector and dot product with one of V or B, I should get 0 because they are perpendicular to each other. So, all that is remaining is, so I am going to club Q times V and E, and if this region has a charge density of n charges per unit volume, so we can say that the net rate is n q v dot E, right. But this you can go back to our discussion on resistors, right. So, the first term NQV is essentially current density, right. So, we have this as J dot E, right. So, we can say that this is the rate of loss of energy per unit volume. All right. So, now we are ready to put back this expression in our equation. Right. So, if I were to combine this into a single volume integral, I will notice that I can actually get a point form like expression This is to say that the integrand has to be 0, right, or dou u by dou t okay. Remember that up to this point we still do not know what u and p are, right, but luckily we have a term that we are quite familiar with so far in this course, the current density and the electric fields, right. So, let us resort to the Maxwell's equations and see what we can learn from there to express this term J dot E, right, and perhaps we can write that as a term that is a time rate of change, right, and whatever that is, that I could equate it to u, and perhaps it has a component that has a divergence term in it, and whatever I see there I could associate that with p, right. So that's the whole hope, right, that we can try to write out the expression for j dot e, and by similarity I can try to find out what u and p can be. So from Maxwell's equation, so let's recall that curl of H is J plus epsilon dou E by dou T, right. So this is the equation in which J appears. So I can take the dot product with E, right. So E dot curl of H is E dot J, which is what we are after, plus epsilon E dot dou E by dou T. Okay. So this last term I can also write this by the famous expression in electrostatics for energy density, right. The rate of change of energy density, we can write this as half of epsilon dou by dou T of mod E squared. Right. So E dot E is modulus of E squared. This is quite simply the chain rule, right. So if I have dou by dou T of E dot E, right, I can do this as I would do a derivative for two functions taken in product, right. So using the chain rule I can say that this is E dot dou E by dou T plus E dot dou E by dou T, right. So we are sort of using this and converting the E dot dou E by dou T as dou by dou T of mod E squared, right. So let's shift our focus to the E dot curl of H. We are going to use a vector identity here, where we have curl of E cross H is E dot curl of H minus H dot curl of E. Why are we doing this? Because remember, I want an expression, right, for P in our energy conservation equation, right, and E dot curl of H is not quite in that form, right. So I would like the divergence of some vector field, right. So I am trying to rearrange this slightly. Okay. and we are going to use the second Maxwell's equation for the curl of E to simplify this. So I am going to say that E dot curl of H is, sorry, this identity is del dot, right? So del dot E cross H plus H dot minus mu dou by dou T of H. Okay, so let's incorporate 1 into our equation here. So remember E dot J, I would like to replace this with a quantity that is a time rate of change of some quantity. So in this case it would be minus half dou by dou T, or maybe I can pull this half inward to 1/2 epsilon mod E squared, and then I have minus dou by dou T half mu mod H squared right, that's coming from this term. And then I have plus del dot E cross H. Okay, so I am writing this by combining the two in the brackets. Right. So all this mathematics has really been about trying to get E dot J in the form. So remember from the prior slide we had E dot J is minus dou U by dou T and minus gradient of P, or divergence of P, sorry. So I am going to equate this to minus dou U by dou T minus divergence of P. Okay, so I am just going to compare these two equations, one that was obtained from Maxwell's equations and the other from simply trying to write the conservation law for energy locally, and we can now get the expression for the field energy density and the power flow.